Okay, team, we're going to finish up the fungi. It got cold. Got cold. Here's what we have left to do. We have Deuteromycota, and then we have to talk about a couple of symbiotic relationships involving fungi. And then we'll talk a little bit about what's on the fringes of being a fungus and why it's not technically, or maybe it is, who knows. So the last division is the Deuteromycota, and sometimes we would consider this to be kind of a garbage division. The idea is, if it doesn't make a zygospore or an ascus or a basidium, then we dump it in here. And so what that means is the deuteromycetes, we call them the fungi imperfecti, or the imperfect fungi, because we've never observed sexual reproduction. Because we've never observed sexual reproduction, we don't know where to put them in those other three groups. And so some of the theories are that these organisms used to reproduce sexually, and because they were so successful reproducing asexually, they just gave up on sex. And so we have many species. Two of the most important ones are Penicillium and Aspergillus. Penicillium, of course, as the name, as you could probably tell by the name, is the source of the first known antibiotic. And so we'll talk about these organisms. Now, I will mention they're often allied with the ascomycetes because of asexual reproduction and the similarities that we see when they reproduce asexually. So, depending on the taxonomist and who you talk to, they may be dumped in with the ascomycetes or given their own division. Okay. You are familiar with Penicillium. You've seen it. It is ubiquitous. It's everywhere. And it is typically a blue-green color. Some of the familiarity that you might have with it comes from eating blue cheese, because that's what they make blue cheese out of. So Penicillium roquefortii is what they make Roquefort cheese out of. You've seen it most likely on citrus or pretty much on anything that has carbohydrates in it. It will eat it. It'll attack and eat it. It's opportunistic fungus, and you can see it does have this classic blue-green color. Now, if we blow up these spore masses, and what if we think about reproduction, the mycelium grows, and then it produces these chains of spores like this, these little fingers of spores, and these are called conidia. So conidia are chains of spores, and these things are super prolific. You can see them here, these little fingers. They're super prolific. They can start sporulating within a matter of hours almost. I mean, certainly in 24 hours, they can grow vegetatively. The mycelium can grow, and then they can start making these spores. And, these spores are everywhere. If you swabbed your countertops, you would find these spores. It is a common contaminant of sterile culture. And an allergen as well. Many people are allergic to the spores if you get a whiff of them up your nose. Alexander Fleming was a microbiologist back in the mid-1900s. And Alexander Fleming is very interesting. We'll talk a little bit about him. He was also an amateur artist. And so what he would do, make a little more room here, he would take a Petri plate with agar in the bottom, a nutrient agar, and then he would take a liquid culture of bacteria, and he would grow, he would paint the bacteria on to the agar plate like this. And he did faces, but he also did some nature scenes, maybe a little cabin, with a tree or whatever. Okay, so it was invisible paint, right, when he painted it on, because it was a liquid bacterial culture. But as the bacteria started to grow, you could then see this painting that he made. And he thought this was very clever, and he was doing this kind of in his spare time as a microbiologist. Well, one day he observed when this particular green mold would start to contaminate the plate, as it grew outward, he observed that it would get rid of the bacteria in its wake. And so he said, you know, there would be this sort of clear halo around where this thing was growing, where it had killed the bacteria. And so he postulated that this particular fungus was producing some kind of chemical which was then diffusing through the agar and killing the bacteria. Hence, the first antibiotic was discovered. Well, guess what, y'all? Since that time, antibiotics have been a game changer for the human race as well as for animal husbandry, right? Prior to the discovery of antibiotics, if you had a superficial wound that got infected, there was a pretty good chance it would become septic and you would die. There were just not very good ways of treating bacterial infections like staph. Okay, people died routinely from strep throat. Right, their tonsils got infected. There was no way to treat it, and so now all of a sudden we have a way to treat bacterial infections with antibiotics, and we've been off to the races ever since. Now, two things have happened since the advent of antibiotics. One is misuse by patients, right? And the other is misprescription by doctors. Because of these two things, and we'll talk a little bit more about them, we now have resistant strains of bacteria for which no antibiotic will cure. So misuse, you know, let's talk about misprescription first. You know, when I was a kid and I went to the doctor, unlike today, if I had a sore throat, they would swab my throat and they'd say, well, you may have a bacterial infection. We won't know for a week or so, because they would literally have to culture the bacteria on a Petri plate and see what it was. But they would often be like, but let's go ahead and prescribe you these antibiotics just in case. Okay, well, you know, the problem with that is you are creating this environment for mutation if, you know, if you don't have a bacterial infection. And so then so overprescription or misprescription of antibiotics is part of the problem. The other problem is misuse. So then let's say I do have strep throat and I get a 10-day supply of antibiotics. Usually after 2 or 3 days, I start feeling better. It's very quick. And so then if you're anything like I used to be, you'll say, well, I'm just going to put these in my medicine cabinet for the next time I get a sore throat. There again, you're creating this environment that's ripe for mutants to survive. So the idea is if a few of those, let's say strep bacteria survive because they mutated and you don't take that full course of antibiotic, you then pass those on to the next person and all of a sudden there's no resistance, okay? There's resistance rather to that particular antibiotic. And so they give that person the same antibiotic and it doesn't work. We now have mutant strains of staph and strep for which no known antibiotic will cure. And this is a serious issue, okay? So that's penicillium in the Deuteromycota. It's perfectly happy just to make these little conidia or conidia spores, as the individual spores are called, doesn't have sex, no sexual reproduction. And then we have kind of the black sheep of the Deuteromycota, which is called Aspergillus. Aspergillus causes a disease in animals. It's an allergen, but it can also, in certain individuals that are predisposed, either through immune disorders or just genetically predisposed, it can cause a disease called aspergillosis, where literally in your sinuses or sometimes in the lungs, a fungal ball will begin to grow. So one of these spores lands and it begins to grow. We can look at the next slide. Actually, this is it growing on a Petri plate. it's typically black and white. Anytime you see black and white mold, not a good thing. Here's a sporangia of, or a spore producing, or conidia producing structure of this. And you can see all these many spores it's producing. If one of those spores happens to land or get up in your sinuses and you're predisposed, it can start to grow and it can produce this fungal ball. And it's very, very difficult to treat once it starts. In some cases, they have to invasively go in and try and cut it out, which is not a good thing. It almost becomes like a cancer in the individual. Sometimes these individuals will end up being on drip antifungal compounds for months just to try to deal with the infection. So Aspergillus is one to avoid. If you live in a moldy house, a moldy basement, for example, you would expect for there to be a certain amount of penicillium and Aspergillus and Rhizopus spores in there. That's normal. The mold police, it can be a scam, just so you know. They come and they say, oh, we want to test your house for mold, and then they'll put a Petri plate out for 24 hours. And of course, there's going to be lots of mold growing on the Petri plate. It doesn't take long for those spores to germinate and grow. And then they show you the plate and they're like, oh my God, you have mold problems. Well, that may or may not be the case. Everyone has mold spores in their house, okay? But again, high levels of Aspergillus in the air where you're living is not a healthy thing. Okay. Now, what about the fringe? There are the chytrids, and the Chytridiomycota is often put into the kingdom fungi because they're all the world like a fungi, like a fungus. They grow, they live in water, but they grow in, they have mycelium, they have hyphae and filamentous hyphae. The difference though, is they produce zoospores like an algae or a mastagophoran, a flagellate. So, if we strictly say fungi are non-motile, they don't have a motile stage in their life cycle, then we would exclude this group. There's one called ick, which attacks fish in aquariums, and many of them are parasites of aquatic animals because obviously that's where, because they live in water, okay. And then there's the Myxomycota, which are the plasmodial slime molds, which are very bizarre. And they kind of have this giant amoeboid stage and also a fungal sporangia producing stage. And so there again, we don't quite know what to do with them. And we can, it's worth looking at a few pictures at least of the slime molds. The most common one around here is a bright yellow. And you've probably seen them growing. I can show you. We can look at lots of images of them, of course, on the internet. Most of these are the ones that we most commonly have. And you can see, there's this very strange this thing literally creeps along. It's like a giant amoeba and it moves. It'll sometimes crawl up walls, which is very bizarre. But then at some point, it begins to make sporangia, and you can see these sporangia that it's producing here. And then, so at that point, it's more like a fungus than an amoeba. Well, I don't know what I've done here. Here you go. So here are the sporangia being produced, and here's the vegetative, more amoeboid stage of the life cycle, okay? So those are some oddball things. Oops, what have I done? Oh, here we go. We're all good. Okay, so now, two last things to talk about. And we're gonna just do a little chalk and talk on these two things. Well, actually, normally in a classroom, I would have samples of these. And so for the first one, which we call lichens, it will make sense to look at some images. Normally, I would pass little lichens out for you to look at. But we will look at some pictures online real quick. You've all seen these. They're ubiquitous. They're everywhere. You can see here's a nice image of some lichens. Let's see if we can get this one image to pop up. I hope so. No, maybe not. Oh yeah, there we go. Okay, so there are different kinds of lichens. There are leafy lichens and shrubby lichens, and you can see both of those here. Here are the leafy ones and the shrubby ones. And then there are crustose lichens or encrusting lichens, which are the ones that grow on rocks like this. Okay, so we'll talk about these three different types. Okay, and we'll talk about, it's a symbiotic relationship. So we'll talk about, what is in this thing here. And we'll just do a little chalk and talk. It's probably the best way to do it. There's the Botany-Mycorrhizae life cycle. Right, zygotic life cycle, zygote, meiosis, basidiospores. Okay, so lichens. They come in three varieties. They come in encrusting or crustose, which we just saw on the rock. They come in foliose varieties, which are leafy, and fruticose, which are shrubby. And morphologically, these are describing them. What is a lichen? Well, it's a symbiosis, mutualism. So we'll say mutualistic symbiosis. And so now immediately we know there's two organisms and they both somehow benefit. And what are the two organisms? Fungus. And the fungus is usually an ascomycete. And a green algae. Okay, so we have green algae, unicellular green algae, and a fungus living intimately together. We could draw this lichen. It's almost like a algae sandwich. You got the fungus on the outside, and then you got these green algal cells on the inside. And if you cut this thing open, you would see this. Okay, and so keep in mind, we have two different kingdoms represented here in this symbiosis. We have the kingdom fungi and the kingdom protista. And so now you think about, okay, if it's mutualism, they both benefit. Well, how does the algae benefit? Where do algae usually live? In water, right? And so how the algae benefits is the algae now has a way to colonize land, to live on dry, bare rock that it could never live on, because the fungus provides it with a certain amount of protection from desiccation. So we're going to say protection from desiccation. What's desiccation? Desiccation is drying out, right? Okay, so that's what the algae gets. The algae gets to live on land, which is a big deal for an algae that normally would be stuck in the water. What does the fungus get? Well, the fungus should be really obvious what the algae can do that the fungus can't do. The fungus gets sugar, right? Or photosynthate from the algae. How cool is that? Now, as far as reproduction goes and classification, we typically classify the lichen based upon the fungal component, because the algal component is all pretty much the same little green balls, right? The way these things reproduce is very bizarre. They reproduce together, and what you have are individual algal cells, and they form these little volcanoes, and erupting out of these little volcanoes, the volcanoes are called souridia. And I don't think you have to know that word, but what erupts out of this volcano are individual algal cells, and wrapped around the algal cell is a little piece of fungal filament like this. So both species erupt out, and wherever they land, they grow into a new lichen. Lichens are colonizers. They're some of the first things to colonize new land. For example, when you have glaciers that are moving and they're exposing earth that hasn't been unexposed to the air because it's been under ice for, thousands or millions of years, lichens are some of the first creatures to come and live there. If you look along streams, you can see the lichen line, which is if there's a stream here and there's a tree, you'll notice there's a certain level where the lichens start to grow, and this is called the lichen line. And this is a good indication of the flood level of that particular river, because lichens don't do well submerged in water for more than 24 or 48 hours. Okay. The other thing that we use lichens for is as indicators of pollution. So they are very good at, or they're not good at, but as a consequence of their life form, they absorb pollutants out of the air. And so you could literally take some lichen and crush it up and analyze it and know what kind of air pollutants there were in that particular region. The lichens are some of the first things to die when the air pollution gets to a point where they can no longer tolerate it. So when the lichens start to die, then we know, other things might be next. Okay. So it's an important symbiosis. Anytime we talk about a symbiosis, you want to know what's the nature of it, who gets what, and who gives what. In this case, the algae gets protection from desiccation and the fungus gets sugar. All right. The next one is called Mycorrhizae. And I can't stress to you how important this is. This interprets from the Latin as fungus root. Okay. And what we know is that this is a relationship between vascular plants and fungi, mostly basidiomycetes, but ascos will also form mycorrhizae. In fact, taxonomists have pulled out all the fungi that produce mycorrhizae and put them in their own division, which is kind of wacky. Well, what we know is 80%, at least 80%, we'll say greater than 80% of all vascular plants form these relationships with fungi. And so if we draw a tree with its roots like this, and we draw another tree over here, nice trees, huh? It's very Halloween-y. It's Halloween today. And then what we see are that these fungal filaments are literally attached to the roots, and they also can connect adjacent trees together, like almost like telephone lines. Okay. The drawing shows what they did. Increase in surface area equals absorption of nutrients, particularly phosphorus and water. What I'm saying is this fungus is really good at scavenging phosphorus from the soil, and it passes the phosphorus onto the tree. It literally fertilizes the tree, and it can also provide the tree with water. So that's a big deal. And then, what does the tree give the fungus? Well, believe it or not, at least in some types of mycorrhizae, these fungal filaments are tapped into the phloem. They are literally sucking sugar out of the tree. It's a trade-off. The tree has to give the fungus sugar, but the return is great. If you look at pictures, and we will in a second, of inoculated with mycorrhizae versus uninoculated pine trees, you can see the inoculated ones grow at a rate of about 3 times that of the uninoculated ones. And so these help the trees to grow. As we say, most vascular plants form these relationships with fungi. Okay. And so, the fungus gets sugar. And plant gets increased absorption of nutrients. Okay. So here's the crazy thing though. When the mycorrhizae connect adjacent trees, what we believe is that this allows for a communication between these trees. And you know, they've done all sorts of studies where, for example, they might put a net around this tree and then put some insects that herbivorize or eat the tree, right? And what will happen is this tree will start to produce anti-herbivory compounds, but so will this tree. And so somehow this tree told this tree, hey, we're getting eaten over here. And the most likely candidate for how that happens is through these mycorrhizal connections. They can send messages back and forth. So plants can definitely communicate with each other. And, you know, this is an interesting phenomenon. Okay. Folks, oh, here's an encrusting lichen. We looked at it before. Okay. That pretty much does it for the fungi. You know, we've talked about lots of cool stuff, and I hope you've enjoyed the conversation on fungi. I find them fascinating. What we have left to do for this next unit in test 4 is to cover the spore-producing plants. These would be what you would know of as mosses and ferns. And then, so we have probably 1 to 2 more lectures, and then we'll be done with this unit and we'll have our next test. Okay. Well, I hope you've had a good day, and I will talk to you soon.